Our next topic is transformations of functions. Transformations take a function we know and stretch or move it around the xy plane. If we know the formula for our original function, we can make changes to the formula to produce the formula for the transformed function. Transformations are best understood through examples, so let's look at our first problem. Consider the function f of x equals x squared plus 2x plus 1. Here's a picture of this function. You can get this picture by plotting some points or by completing the square and finding the vertex of the parabola. Problem 5 asks us to take this function and translate it vertically by 3 units. This means we want to shift every point on the graph of f up by 3. Let's do this now and call the new function g. The formula for g is obtained by adding 3 to the formula for f. That is, g of x equals f of x plus 3. Or x squared plus 2x plus 1 plus 3, which is equal to x squared plus 2x plus 4. To see that this formula is correct, let's compare g of 0 and f of 0. F of 0 is 0 squared plus 2 times 0 plus 1. That's 1. While g of 0 is f of 0 plus 3, so it's 1 plus 3, or 4. So the point above 0 on g is 3 units above the same point on f. In general, if we want to shift a function f up by a units, the new function g will have g of x equals f of x plus a as its formula. If we want to shift g down, we simply make a negative. Our next problem asks us to take the graph f of x equals x squared minus 1 and stretch it vertically by a factor of 2, and then write the equation for the new graph. First, let's draw f. F is obtained from the graph of y equals x squared by shifting its graph down by 1 unit. We can see this from the formula for f. Now that we've drawn f, let's stretch it vertically by a factor of 2. We do this by taking any point on f and multiplying its y-coordinate by 2. For instance, 0, minus 1 is on the graph of f. It's the vertex of the parabola. If we double its y-coordinate, we get 0, minus 2. This point is on g. If we take the point 1, 0 on f, then since the y-coordinate of this point is 0, doubling the y-coordinate does not change it. So the point 1, 0 is on g as well. Finally, the point 2, 3 is on f. So 2, 6 is on g. Let's fill in the curve for g. The equation for g of x, the height of the graph g above x, is 2 times the height of f above x. So g of x is 2 times f of x. So g of x is equal to 2 times x squared minus 2. That's our formula for g. In general, if you want to stretch a graph vertically by a factor of a, then the new function is obtained from the old function by multiplying by a. If a is negative, then the graph gets reflected vertically before you stretch it. If a is a fraction that's less than 1, then the graph will be compressed vertically. Now that we've seen how vertical transformations change the formula of a function, let's look at a formula and see if we can figure out how it was produced. Problem 7 asks us to draw the graph of f of x equals 3x squared minus 1. This formula looks like it came from the graph of y equals x squared and then was stretched and translated. Since the coefficient of x squared is 3, it looks like there was a stretch by a factor of 3. Since the constant term is minus 1, the graph was shifted down by 1 unit. We have to be careful about the order of the translation and the stretch. If we translate first, we get y equals x squared minus 1. Stretching this function by a factor of 3 multiplies by 3. So we get y equals 3 times x squared minus 1. So y becomes 3x squared minus 3. Since 3x squared minus 3 is not the formula for f is not obtained by translation first and then stretching afterwards. If we work in the opposite order, we stretch first to take y equals x squared to y equals 3x squared. Then we translate this down after to get y equals 3x squared minus 1. This is f. So let's draw the picture that corresponds to these operations. We stretch first to get y equals 3x squared. And then we translate down by 1 to get f. So this is the graph for f. Now we've covered both vertical translations and vertical stretches. We'll see in the next two problems that formulas for horizontal translation and horizontal stretches are a little more complicated. Problem 8 asks us to translate f of x equals x squared minus 1 to the right by 2 units and write out the formula for this new function. Let's quickly draw the graph of what this would look like. The vertex, which was previously at 0, minus 1, now moves to 2, minus 1. And the point which was at 2, 3 moves to 4, 3. The question is, what should the formula for g be? One guess might be that g of x should equal f of x plus 2. This is incorrect, and let's see why. G of 2 should equal minus 1. But using this formula, g of 2 is equal to f of 2 plus 2. It's equal to f of 4, which is 16 minus 1 is 15. The correct formula is g of x equals f of x minus 2, which equals x minus 2 all squared minus 1. Let's test this again. If we plug in g of 2 using this formula, we get g of 2 equals f of 2 minus 2, which is f of 0, which is minus 1. Here you can see why this formula works. We want the height of f at x equals 0 to now appear over x equals 2. So when we put x equals 2 into g, we want it to compute f of 0. So we want g to subtract the translation from x before putting that value into f. The general rule for translation to the right by a units is that y equals f of x becomes y equals f of x minus a. You should try and remember that horizontal translations are the opposite of what you might expect. Problem 9 asks us to stretch the graph f of x equals x squared plus 4x plus 4 horizontally by a factor of 2. First, we should draw this graph. If we factor f, we get f of x equals x plus 2 all squared. You can see that this is a horizontal translation of y equals x squared by 2 units to the left. We know it's 2 units to the left because we're adding 2 to x rather than subtracting 2. So here's our graph for f of x. Next, to stretch by a factor of 2, the vertex moves from minus 2, 0 to minus 4, 0. We're doubling the x-coordinate. Also, the point 0, 4 stays on the y-axis since doubling the x-coordinate, which is 0, doesn't change the x-coordinate. So the point doesn't move. So we can fill in the graph of g as shown. The formula for g comes from replacing x with x divided by 2. That is, we replace x with x divided by the amount of the horizontal stretch. So, g of x equals f of x over 2, which is x over 2 all squared plus 4 times x over 2 plus 4. And that equals x squared over 4 plus 2x plus 4. Notice if we evaluate g at x equals minus 4, we get g of minus 4 equals f of minus 4 over 2, which equals f of minus 2. Thus the height of g above x equals minus 4 is the same as the height of f above x equals minus 2. So we've made the formula correctly. In general, if you want to stretch the graph of f horizontally by a factor of a, the formula for the stretched graph will be y equals f of x over a. Like horizontal translations, this seems to be the opposite of what you might expect. If you make a negative, then there will be a horizontal flip before the stretch. If a is a fraction between 0 and 1, then the transformation is really a compression of the graph. Our final problem on transformations is to graph the function f of x equals x over 2 plus 4 all squared. Much like in problem 7, which was for vertical transformations, we're going to have to sort out the order of the horizontal transformations which produce f. We see that the coefficient of x is 1/2. This corresponds to a horizontal stretch by a factor of 2. We also see that 4 is added to x over 2. So it looks like there's been a horizontal shift to the left by 4 units. The shift is to the left since 4 is positive. Remember, everything is backwards for horizontal transformations. So if you start with the function y equals x squared and translate first, we get y equals x plus 4 all squared. If we scale next, then we replace x with x over 2 to obtain y equals x over 2 plus 4 all squared. And this is exactly f of x. We know what y equals x squared looks like, so let's shift it to the left by 4 and draw y equals x plus 4 all squared. Finally, we can take this graph for y equals x plus 4 all squared, and we can draw f of x by scaling it horizontally by a factor of 2. You should go back and check that if you stretch first and then translate second, you get a different function. You don't get f of x. The function you'll find that you get is y equals x plus 4 all divided by 2 and then all squared. Here's a summary of the transformations we've learned. To translate vertically, that is to shift a graph up by a units, we add a to the outside of the function. To stretch a function vertically by a factor of a, we multiply the function on the outside by a. To translate a graph horizontally, to the right by a units, we subtract a from the function's argument x. So we substitute x minus a into the original function. Finally, to stretch a graph horizontally by a factor of a, we plug x divided by a into the function. When you come across a formula for various functions, these rules should help you visualize where the graph is placed in the xy plane and the scale which it takes.